That's a duck, folks. And this is a duck house. The duck house has a roof. The roof is a plane. How did I support this roof on this duck house? Well, instead of using a single post in the middle canted at an angle, which would be hard to build, I supported this roof with two beams. Each beam is a straight line. This is one piece of wood supporting the front of the roof. It's a straight line. If you go to the back of the roof, the top of that wall also forms a straight line. Those two straight lines are parallel. And if you have two parallel straight lines, there's exactly one plane that includes both of them. And that's the plane of this roof. And this is a goat. And the goat has a goat shed. The goat shed roof is supported in the front by a single straight beam, straight line. In the back, the roof is supported again by the top of a long straight wall. Two parallel lines that define one and only one plane that passes through both of them. But suppose I wanted to have a shed that was standing on, say, 4 vertical posts. I want to go cheap. Let's start with 2 vertical posts. I think you know what's going to happen if I put a roof on that. Well, it will hold it up, but because of the fact that there are only 2 points that the roof is resting on, there are an infinite number of planes that can rest on top of those 2 points. So no one position is going to be stable. So what do I need to make it stable? Yeah, a third point. So I need a third vertical post to even have a hope of making this stable. Prince, you're knocking over my post. Knock it off. Watch out. So I'm going to put a third post back here. Just going to pound it in some random depth. And let's see how our roof works now. Hey, that's stable. There are 3 posts holding up the roof. And that means that there are 3 points that define a unique plane. There's only one plane in the universe that will pass through those 3 points on top of those 3 posts. But if I want to have 4 posts, you know, for added strength, where do I put it and how high should it be? Well, let's try putting in a post to see what happens. This is the 4th corner. Just knock it in some random depth. And we'll put our roof back on. That's stable. Oh, wait a second. It's also stable here. There are 3 points that it's resting on, and now a different 3 points. If I want to have all 4, and let's say these 3 I know I want to have first, where do I need to put the 4th one? All right, maybe this is the better one. If I've got these 3 that are stable, where or how high does this post have to be in order to make all 4 points? So you can't just pick that 4th point, that 4th post height at random. It has to be carefully chosen. And we can do it by trial and error, but I bet there's a way to use math to predict how high that post needs to be. Let's go take a look. What?
So here we are looking at a goat shed problem with right now 3 separate posts. I have a post that starts at the origin, that's at 0, 0, 0, and it's 9 feet tall. I have a second post that starts at the coordinate 0, 18, 0, and rises 8 feet. And then a third post, post C, which begins at 16, 18, 0, and rises for 10 feet. I want to put in a 4th post starting at 1600, but I need to know how long that post has to be in order for it to lie on the plane that's formed by posts A, B, and C. So to do this, I really need to figure out, based on A, B, and C, what plane actually would rest on top of those 3 posts. How would I find that plane? Well, the trick is to use something from vectors. There's a vector multiplication method called a cross product, which is going to be very handy for this. And in order to use that, what I need to do is come up with vectors that model the edges of the roof that I know about. And the 2 edges that I know about are the one that goes from point B to point A, and I'm going to model that as a vector BA. So BA is going to be from point B to point A. So in order to figure out what that vector is, I need to know the coordinates of those 2 points. Be 0, 0, 9 at the top of the post. And post B is 8 feet tall, so it's going to be 0, 18, 8 as its coordinates. And then post C at its top, where am I going to write that? Let's say right here. Okay, is 16, 18, and its height is 10. It's a tall post. Now, the other vector I want is to go from B to C. So I got my 2 vectors representing the edges of the roof. Now, let me go back to writing out the vector. So the vector BA, what you do is you take the coordinates of the end point, which is A, and subtract the coordinates of the beginning point, which is B, and that'll give you the components of the vector BA. Well, the difference of the x coordinates is 0 minus 0. The difference of the y coordinates is 0 minus 18, and the difference of the z coordinates is 9 minus 8. So that vector is simply 0, negative 18, 1. And then vector BC, the difference of we're going to be taking the c coordinates minus the c coordinates minus the b coordinates, right? So that's going to be 16 minus 0, comma, 18 minus 18, comma, 10 minus 8. And that gives us the vector 16, 0, 2. Okay, so I've got the components of these 2 vectors, BA and BC. Now, the cross product, which is written like this, BA cross BC. Looks like an ordinary multiplication symbol, but it's kind of special. It's for multiplying vectors. And this is different from the dot product. The dot product was pretty easy to calculate by hand, gave you a single number as a result. The cross product is more complicated to calculate, and it gives you a vector as a product. And that vector, one of its properties is that it's perpendicular to the 2 original vectors. So this is a neat trick for finding the equation of the roof, because the equation of a plane is going to have coefficients that are proportional to the components of a perpendicular vector. So if we come up with a perpendicular vector, we can get the coefficients of the roof. Nifty. Now, like I said, computing a cross product is a little complicated, and we're going to use Google Colab for it. So I've already figured out what this cross product is based on these 2 vectors, and that is this vector, negative 36, 16, and 288. Now think about it. That's a vector that has most of its work being done by the z-coordinate, 288. So it's predominantly straight up, a little bit to the negative x and a little bit to the positive y. So it's not quite vertical, but it's very, very long, and it's mostly up. So if I wanted to sketch that in, I don't have enough room here on my graph to really do it, but it would be in that direction-ish, and that would be the cross product, BA cross BC. Okay, now we can work on the plane equation. So the plane equation is going to be formed using the components of that cross product, that vector which is perpendicular to those 2. So I'm just going to write down those coefficients. It's going to be negative 36 times x plus 16 times y plus 288 times z equals that mythical d parameter. So again, I'm just taking these numbers and using them as the coefficients in my plane equation. Very simple. Now, to figure out what that D value is, I need to use a point that's in the plane. And a nice easy point to use that's in the plane is the top of post A because its coordinates are 0, 0, 9. So let's plug those coordinates into the plane equation and see what we get for D. So it's going to be negative 36. The x coordinate at the top of A is 0, plus 16. The y coordinate at the top of A is 0, plus 288 times the z coordinate at the top of the post, which is 9. And so all we have here is actually, so the first two terms are times 0. They go away. It's just the third term, 288 times 9, which is 2,592. So our plane equation ends up being negative 36x plus 16y plus 288z equals 2,592. That's the equation for our plane. Now we want to know how high does our our fourth post have to be? And we know that our fourth post has an x coordinate of 16 and a y coordinate of 0. And it's going to go up here. We just don't know what the z coordinate is. So we know what the x is. We know what the y is. We just don't know what the z is. So all we need to do is solve this equation for z, right? Well, let's do that. So we're going to have 288z equals 2,592 plus 36x minus 16y. And we'll divide both sides by 288. So we get that all over 288. Okay, now that means I've solved for z, and actually for any x and y coordinate, any place on the floor of this building, I can calculate what the height of the roof is. That's what this equation does for me. And in particular, I want to know at this point, which has coordinates x, 16, and y, 0, I want to know how tall the roof is. So let's evaluate the right-hand side under those conditions. Z equals 2592. The x coordinate is 16, so it's going to be 36 times 16. The y coordinate is 0, so this negative 16y piece disappears. And this is all over 288, which is 11 feet. So finally, I can sketch my last piece here. There we go. So the coordinates at the top, this is post D, the coordinates are going to be same as the base, 16, 0, and then the Z coordinate is its height, which turned out to be 11 feet. So the Z coordinate is 11. So now I know how big to make that fourth post. And now I could see that I've got all four posts, and I can imagine the plane, the roof on top of that, and my goats will be dry.